Thank you one more time, Mike, and welcome.
Thanks a lot. Thanks for the introduction, and thanks that I have the opportunity now to be affiliated to MDU and show a little bit of what I have done in the last 10 years, more or less. So to me, myself, so my name is Maike. Right now I work at Alfa Laval Technologies and I'm employed in Lund, but I will also involve a little bit of an Alfa Laval presentation later, so you will learn a little bit more about the company and the challenges we have there. But for now, so what will I present today? So it is robotics. So what is it? So for me, it brings the most value if we can. Yeah. Is it okay?
I'm joining you right now. I'm down in the lobby.
Perfect. Thanks a lot, Gustav. So, yeah, robotics. So to me, so it brings the most value if we can have it outside somewhere in real-world applications. So what is it to me? For example, in production, in assembly, or in hospital environments, construction environments, or even in our own homes. But how do we get the findings we have from research out into real-world applications? I think this is a difficult question, and I would like to show you a little bit what I have done the last years and call it applied robotics, so from research to industry. No. So, but how it started, so who I am and why am I here today? So I come from a region, the Rhine-Ruhr area in Germany, where we have 11 million citizens on 7,000 square kilometers. And you who live in Sweden here, so you have the same amount of people, but on 45,000 square kilometers. So you can imagine the area was crowded, loud, and very multicultural. So a nice area. So whether you like it or you hate it, but I liked it. So, and what did I like the most when I was small? So I loved to go to the airport and watch the airplanes starting and landing. And then I thought one day I would like to work in this environment. So what could be a possibility to work in this environment? I thought working here in the tower could be one option, being a flight controller. But then, unfortunately, it didn't work out. But from my nowadays perspective, I would say, luckily, it didn't work out. So then I thought, what can I do else? Maybe study flight engineering. Yeah, but something, then I had to leave this area. So for something I was not sure if I would like to do it or not. Then I thought maybe it will be mechanical engineering because there was a university close by in Bochum where I could study mechanical engineering. And for me, so this was a super good time because I studied here with University Bochum in those buildings here in the back. So there I spent 5 years of my life, more or less. And it was a lot of freedom compared to the school system we had before, which I loved a lot. And then I got a lot of insights into areas which I have not been dedicated before. So I had a very good mechatronics course where I got in touch with microcontroller programming the first time, and we disassembled vacuum cleaner robots, for example, those days. So it's about more than 10 years ago now. So we had those vacuum cleaners which were able to change the path when they hit something. And with the assumption was that it should go left or right, but those days it was just able that they went the right way. And then I got interested, so how does it work? So why does it work wrong? Then I was also in robotics, programming, simulation, offline programming, and then production environment was really, really nice. And then when I had finished my studies, I went further, so one turn further on the Rhine-Ruhr fast highway, the TU Dortmund connected to the RIF e.V. So what is it? So I was looking for a job as a in production automation. And there they had a share for robotics and production automation, which was also connected to this research institute, so for research and transfer. So they had the possibility to make research and also had a good connection to industry those days. So I could work 3 years, more or less, in this environment, kind of a research project engineer. And I started with a research study about medical robotics those days. And I worked on a project which was called ManuSurf, which I will present to you a little bit more. because this is human-robot collaboration topic, which could be interesting for here. And then I also had the chance to acquire funding for my PhD project, which we handed in at KMU Innovativ those days, which is a little bit similar to Vinova, what you have here. Manoserve, what is that? So Manoserve, the idea was to come from manual processes to industrial service robots. But how to do this? And especially for SMEs, because what we experienced that it was really, really hard to get automation, specific robotics automation, into SMEs where they don't have experts within this area. So it is hard to identify a process. Is it good for automation or not? So we designed a support system for the planning and decision taking for those systems. And the idea was that you can describe your process, put it into a system, and get a suggestion out for possible automation solutions and how to match it together to get an outcome of it. And to do this, we described processes with MTM. I think you have heard the ones from you who are from the production environment. And then we enriched it with specific attributes to make it possible to translate it into PDDL so that we could feed a planning and decision system with that and getting an outcome. But how to start, how to design a database for that? So we started to collaborate a lot with our partners regarding use cases, to have a wide range of use cases to define those enrichment for the process description language on. And we had 3 main use cases. The first one was in assembly of light switches. The second one was equipment of machines for blowing of plastic bottles. And the third one was in farming industry about autonomous cleaning and littering of cubicles. Here you see a first simulation of how a solution for the first use case could look like. And here we had a lot of challenges. For example, working in this environment, what does it mean? Is the highest IP class enough to handle all the material you have to handle inside a stable of cows? Or how can we clean the system afterwards? Is it possible to have the system working while the cows are around, or do they need to be outside always? So this was, or will a cow think it's a toy and climb on it? So those were questions which were not really just related to the automation, but also a lot around the peripheral area. The second use case, it's about the light switch assembly. And there we thought those days, so how to divide. So the station before was completely manually, and then we thought it could be a hybrid station. And while we were working on this concept, the new standard, the ISO 15066, came out for collaborative robots. And then we had a draft before it was out, so we were very happy to have the opportunity to work with that and continue with that. And those days there was a lot of research going on. So what is a task a robot should do, and what is a task a human should do, and how to divide that. And there we thought there was also a lot of research. So there was one person having a full PhD just about the definition, what is a robot task, what is a human task, and how to make a hybrid line or hybrid assembly station. The third process we had was the spike changing process. And here you see, so sometimes for blowing plastic bottles like this, so you need to equip a machine with a lot of spikes. And when you change to another bottle production, you need to change those spikes. And this is a really unergonomic task and with a specific movement. So how could the robot help there? So for example, if you need to change every day, so making this a worker is not really, really good. So this was one of our cases too. But how could we realize one demonstrator for all those different use cases? So we chose a robotics platform those days, connected with a UR5 on top of it to have the possibility to have all use cases in a lab environment and to have it movable. But then we said, yeah, now we have this movable robot. So, and we have just one case where we really need a moving robot. So what can we do else? So maybe we use the mobility to make something else out of it. So we designed a third use case together with another company. And there it was about the, vacuum cleaner handling, because they had a production line which was hybrid, and then at one stage they had a really unergonomic process. So the worker had to lift out the vacuum cleaner from the fixture and put it on the side and then pack it. But since the vacuum cleaner, I guess everybody of you has one home, is 5 kilo, it's not super heavy, but it's not really easy to handle. So, and then we thought maybe this could also be a good collaboration station for our case. And on the right, you see a possible hybrid solution. So the robot lifting the vacuum cleaner and the human packing this. And then we tested it in the lab environment with a really, self-made gripper. So it was just 2 hooks from Bauhaus screwed together at the end effector of this robot and lifting it out. And there were, of course, we were not allowed to make any scratches on the product. So you had to cover also a little bit. And what you can also see very good is in the fixture, so the place you have to get in was also very limited space for that. Yeah. And a little bit shaky, but in the end, so this worked. And we also had tests in the production environment. And those days it was when we came there first with this robot, the workers were very, very afraid. So they were walking around, now this robot will take our job. So, but this was not our intention. So our intention was to have it as a supportive device in an area, not as a replacing device. But then another idea, because this vacuum cleaner process had a lot of other stations too. So it was inline quality, assembly on another station. Then we thought maybe it would be good to have kind of a jumper, so which you can call when you need it, that it can help if a part is missing or so. But so I think here it was more about the concept, not the realization. It took many, many years more until you have seen it in other research environments that it was realized. Or even in production, I don't know. It might come, but it's not state of the art today. So it just goes somewhere, picks something, and brings it where it is needed. And of course, to make this efficient, it needs to be much more faster. But this was the ManuSurf project in general. Then afterwards, so I didn't finish to work on this project until project end. So I switched back to Ruhr-University Bochum to make my PhD there. And this contained 2 parts, one more research part with an evaluation system and another very practical part to make a device, but I will show you. The funny thing is here, so the share where I made my PhD was exactly the share of production systems where I had already written my bachelor thesis. So I came back into an environment where I had been before, so meeting people which I have studied with, so came back in a really good environment for work. And the main topics of this share were, robotics, assembly technology, and manufacturing technology, those days when I was there. But now you see on the picture, so there's much more today. So they expand a lot. So the topic in this area gets more and more relevant. But my PhD, so in Germany, where I have made it, we call it Doktoringenieur, a little bit more fancy maybe. And Frau Doktoringenieur, yeah, this sounds very, very crazy. And the PhD consisted of 2 parts, like I said. The first part was make a methodology for analyzing the automation potential of manual therapy methods. And the second part was the automation of a selected manual therapy method. here it's a new application area, so it's rehabilitation robotics. Let's see what it is. The first step, to make the evaluation system. So in the first step, it was like, since I had worked those years in the MANUSURF project and we had this difficulties to get the knowledge out, so where is potential for automation, I thought it is the same in this environment. It's even worse. So you have a lot of therapy methods which are performed manually, but which could be supported very, very good by machines. So, but how to get it out and how to evaluate if this brings value or not if you automate that. So I built classes, defined criteria, and did a lot of stuff I will not show in detail now because I think this would take too long time. And then I put it into a software tool. Those days it was with MATLAB, they had an app possibility, an app builder. So there you could just choose, so what kind of the body do I treat and for what kind of patients, in which stage of rehabilitation is this patient, and afterwards you get an answer. So if this is possible to automate anyhow or not, and if yes, if it would make sense to do this. So, and it was really easy so that a therapist could just click him or herself through to get an idea if this is something you could get support with. Now, this is the part where we started to build the therapy device. How to start? So the method you see here, it was called individual rhythmic movement initiation of patients with neurological diseases. And what you see here, this is Steffi. She was a therapist in our project. She is transferring a motion onto the pelvis of the patient. The patient here is Bernd. He was the founder of the ambulant rehabilitation center where we work with. He had a stroke, and caused on this, he and his wife, they built this rehabilitation center. So they were so they were open to make this public, what happened to him. And so the movement Steffi puts onto his pelvis is the movement of the three-dimensional lying aid. And this is the same movement like you do with your pelvis when you walk. And doing this with high repetitions helps to relearn movement. And this is the key here too. So you need to do it with high repetition. But when you see the therapist, at this stage she was already 50, and she said, it's super heavy. So I have 30 minutes for a patient. I need to lift him on the bed. I need to put him on the pillow. Then I need to move him. You see, so this is not a really ergonomic position to be here and move all the time. And then I have those heavy guys, say 100 kilo and more. So I would love to have a machine. And then I could just focus on the patient and interact with him, because this is so important. Sometimes it's the only time of the day when they come out from home, so they need this interaction. But here I'm so occupied with moving, maybe a machine would be good. And then, because when you move the same movement, which you might have lost because you had a stroke and half of your body is lame and cannot move anymore, then it is possible to transfer the movement via the spine into the brain and reconnect synapses, which were destroyed by a stroke, for example. But you have to do at least 10,000 repetitions or so. So you need to train a lot and a lot and a lot. But if you hear that, this sounds a little bit esoteric. So you just need to move your hip and then you can walk again. Okay, I was the same. And then I thought, I need to track this motion and see if this is really the same motion. So I did put myself one of those X-Sense suits on. And I walked to see if this is the same. Then I made this earbun method with myself to compare. And I also put myself on a horse, because this was also related to a therapy called hippotherapy, where you just ride on a horse and then you have also the same movement of your hips. Very often used for people with other neurological diseases. And in the end, of course, it was also fun, but we also got an output. And yeah, don't look too much on it. But what we could see is that there are really similarities. Of course, the amplitudes were different and so on. But yeah, based on this, I had a little bit more evidence that I believed this could be something. So the question was how to get now those movement patterns which Steffi applied to the patient out to have this feedable for robotic device. So I built a small functional model, just 2 plates and a cardanic joint in between. The cardanic joint to fix that there is no third rotation, because at this stage of the project we were very sure that we just need 2 degrees of freedom and not 3. And then equip this with sensors of a metris system. No, the videos are not, so they are a little bit. And Steffi put the movement onto the system. Here you see a little bit better. And then we could track them and to have something to relate to. So we had put the watch on top of it, and 0 position is the position where the upper plate is planar to the lower plate. And then you go to the positions of the clock and have 0, 8, 9, 10. You see it on the right side. But there were more requirements, of course, to build a therapy device. Like example, it is not allowed to be too high in case you fall off, or the temperature is not allowed to be more than 43 degrees, because otherwise you can have burnings on your skin and so on. So there were a lot of requirements. So how to put it into a functional model? Here you see we had a base plate, a cardanic joint, sorry for the delay, then a motor gearbox combination with encoders, fixtures, levers, which will appear soon, and linkages, connections again, and an upper plate, and then also a simulation, which was just used to see that we had this 12 degrees we defined, that we don't have collisions. So a first simulation of this. But how to combine now this functional model design from the CAD system and the data we had collected to a real device? So there was a little bit of modeling preparation, smoothing out the data. Luckily, it was a sinus function, so we could play around a little bit more easy with that. And I don't want to go into detail here. So calculating the kinematics, so based on the values we had on the upper plate, calculating which positions the motor needs. And the trickiest point here was to calculate this motion between the lever and the linkage. But it was solved by putting a sphere around the linkage and a circle around the lever, and then calculating intersection points, and just identifying which intersection point is a relevant one, because we had 2. So just limiting the amount we wanted to have, and by this part could be solved. And also a very important tiny detail, that the rotation direction was not the same on both motors. So this was very tricky to explain to other people later, when I will tell you later. And then a test setup. So this was how it looked in real life. Of course, you see there is a lot, but there is no control unit or whatever, so there are still parts missing, but the platform is already more or less full. So I had to put a little bit of control units on the side, and also connections to a PC and so on. But for a first test, this was good enough. So here you see the same technology which we used before to track the movement. And it was able. So I programmed a tiny bit so I could start and stop the platform. And then it made this movement. And what you see, it is on the left, new slide, you see the manual movement. And on the right, you see the smooth data and the new movement, which was automated. So it's much better than the manual movement but not optimal, of course, at this point. So I also did a little bit repetitions, so how it works. And here you see it has still had an obstacle. So when it stopped, and it was not smooth, which is not so good because you don't want the hard stop if you have a patient on top of it. So it needed some more advice from people which worked in this medical device industry from before. So we had another partner from the looking into soft and hardware solutions, and they made some changes. For example, here you see this white plate. This is made of biocompatible material, which is allowed to have in medical devices. And also the control unit we gave to an external supplier of those things, and they made a really small one which fitted inside the part here. And then on the right side you see the movements, which are very, very smooth now and repetitive. So not smooth in the picture here, but in real life. But how to design it now that we can use it? So it needs to be soft. So we had a pillow on top, and it needs to be safe so that patients don't fall off, but it is not allowed to fix a patient so complete that you don't get it off. So if somebody cramps, you need to be able to still open it and put him on the side. And then how to design the GUI. Here, this one was designed with the help of the therapist. So she really said, what do I need? And this was put into the guided user interface afterwards. So it was really, really intuitive to program or to choose what motion should be performed. This was necessary because there were more motions, but I just presented one motion here because I think that's representative enough for the whole motions. And then this was put into a control device. And this is how it looked in the end. So 2 more people from the project and some extra pillows, because in the end the device was much higher than it was allowed. So we had to make a little bit more adjustments on the side. And now you can ask yourself, maybe, why is it for a lying patient? Maybe why is it not for a sitting patient? But this was because there were a lot of studies which were looking into the neuroplasticity of the brain after stroke. And in the first 10 days after such a happening, the brain is so much better to adapt to the new circumstances than afterwards. So if once you will have such kind of an event in your life, you really need a very pragmatic person on your side saying, we do it anyhow, what happens? So just try. So because then you can start with a much higher level to restart coming back into life. Here you see the project partners, but I think most of them I have mentioned already. So this ambulant rehabilitation center, which was really open for robotic devices, but you don't find so many out there which are so open for those type of therapy. Then this Hasomed company, which were in hard and software solutions for medical devices. But today I think they focus a little bit more on the software solution. And we were involved from the share of production systems. And finally, after all this work, I need to wait. I have still a delay in the slides. So I finished. And then So, and as you see, so it was a nice day with a good people. Everybody was happy. At least me, I was also happy to have it finished. And then I took a break, staying in parental leave for a while. And after that, there was a question what to do next. So then I came to Sweden, to LTH in Lund, and started my time as a postdoc in construction robotics. Now you can ask yourself, okay, now you have worked so much in medical robotics and now you go into this dirty area of construction robotics. Why did you do that? But what you could see was, so what I have built was a parallel kinematic manipulator, and what they wanted to do in Lund was building a big parallel kinematic manipulator for construction robotics. And so I had the chance to come here and working in a very interdisciplinary consortium. And they also founded the Swedish Center for Construction Robotics just the year before I arrived. And we had people from computer science, automatic control, architects, construction management people, people from production, from structural engineering. So you really had all those competences which you need to get something up and running in this area. Next slide. So there were different devices we used. On the right side, you see this parallel kinematic manipulator, which I joined in developing and testing and programming and putting it into different applications. On the left, we have an ABB mounted on a mobile platform. And then we also had Spot for visual inspection on construction sites. I will start a little bit with the parallel kinematic manipulator because this was the reason why I came. And here you see, quite soon you will see. So this is the manipulator. So we have 8 links connected to guidances here. And 6 of the links are in parallel, in pairs. Making the translatory movement possible, and 2 linkages which are extendable, making 2 degrees of freedom for rotatory movement possible. And the nice thing here, this is built on those tracks, and they are connected to a support structure in the back, which is built out of box joints, which Mats just presented on Monday to us. So there we had the possibility to reconfigure it very fast. We also thought maybe we want to have it working from top, from the other side, or we have to test, maybe we want to have all those tracks in another relation to each other. So this was really, really good. And then this parallel kinematic was really good because we had a large singularity-free workspace and high rigidity and a high precision. On the left side here, you see the workspace. So with those 4-meter tracks, we could achieve a little bit more than 2-meter workspace in X direction, 1 meter high in, almost 2 meter high in Y direction, and in width a little bit more than 1 meter. So if you think about working on a wall, we could just extend those tracks. With 10-meter tracks, we had a working range of 8 meter in X direction. But I did a lot in masonry, so I think you need to understand a little bit about masonry before we can continue. So what we handled the most in the beginning was bricks and mortar. So in bricks, you see we have a real brick on the left side and an ideal brick on the right side. So those bricks were tricky. So they had an up and down side, a front and a back, which you hardly see when you're not an expert in this area. And they were really hard because they had deviations, so they were not at all good to handle. And then they were porous and dusty. And then we also had this mortar where you need the right viscosity to apply it. But if it's too viscose, you cannot pump it. So a lot of things to get used to. And then a very specific application strategy of the mortar and of the brick, which we had to learn ourselves first in a bricklaying workshop with an expert. So I think this masonry is a real trade and it's a very complex task to automate. But how could we automate? So, and then I adapted tools for the parallel kinematic manipulator to have the opportunity to pick and place the bricks on the left. So we attached 2 additional motors, an AC head, and a vacuum gripper with filter, form, and injector, and also wheel sense camera for computer vision integration. Then for the mortar application, I had an extruder connected to a circular nozzle and a 5-meter long hose and a mortar pump on the side. For wall plastering, even a little bit another tool with a wall plaster board and another nozzle on top. And then there was also this joint raking, where a spindle was mounted into the support tool, in the end effector of the PKM. So how does it look? Here you see how the robot moves over a stack of bricks. It's hard to see here. Then it stops, takes a picture, and adapts to the position of the brick to pick it in a perfect position. And then it does the same when it places it. Because you can imagine, if those bricks are not ideal, we cannot just count 50 millimeter plus 50 millimeter plus 50, but it could be 51, 52 here, maybe just 49 here, and then it's not a planar wall. Yeah, you might wonder about the structure of the wall, but we, as I said, had architects in the team which designed very crazy structures. So then we had to handle this. So the mortar application, here you see that this was really, really tricky. So we had to adjust different parameters. The speed of the robot, the speed of the pump, the viscosity of the material, and then even the pass. Maybe this is not the perfect pass. Maybe we need to go here and make it different. And we spared out the joints in between the bricks. But here we could at least test that it is possible to apply, and also possible to apply another layer of bricks later and have a connection so that it is glued together and does not fall apart. Next, raking. This I liked a lot because raking, when you have a house which is maybe 50 years old, you need to replace the joints in the wall because those are the weakest parts. So if it's wet outside, it gets into the house, and then you have the humidity in the house and you don't get it out. But this is a very dirty task, and it's super hard to find people doing this today. Even people from Romania don't want to come anymore here to do this job for money. So we might need automation solutions. So with this robot, it was really easy to go in and take something out. And also with the structure, it is possible to make this completely automated so that the robot is able to know where are the joints, where are the bricks, and taking it out, it is not a very hard material anymore. So if you just drive a straight line, the rest of the sides breaks away. And then you need to refill, and then you are finished. This is a really nice process. And the last experiments I did just to see if this is possible was experiments with wall plastering. And here you see the material. There was just one pumpable material on the open market for plastering applications. And of course you see, so this material was not perfect because it was not possible to get a constant flow out of it. So I had to stop at this stage manually, start and stop when it stopped to get a good appearance in the end. But what you see, although we started and stopped, we had a very smooth surface. So, and I know those days, so there are other robots on the market doing the plastering inside houses. Then there was another robot, Betan. It was also in the news one day. I don't know if you have seen it 2 years ago, I think, on SVT. So this was the ABB 4600 mounted on a spider crane, where we took off the crane. Then I designed a plate to have a connection between the platform and the robot, which was not easy because there were no drawings at all. And at this time, we didn't have any 3D scanning tools. So it was, in the beginning, me with a pencil and a paper trying to get the parameters, so the dimensions from this plate, into any kind of software. And there we handled in the beginning another kind of masonry, which I just want to show shortly. Those are Finia exact blocks, and those are blocks where you have blocks with an inbuilt isolation, and those are very heavy, up to 20 kilos. And if you think, so people on the construction site, they put a house up with those blocks in 2 days. So they need to handle a high amount of these heavy stones. And there are many processes they need to take. So they need to cut, because quite often it does not fit like it is planned, and then they cut a lot of stones and place them like they need it. They have special blocks here where the isolation is not through the whole block with openings, and then you have a specific tool to apply the mortar and also reinforcement. So what did we do? So we thought, if we want to build a one-story house with such kind of a robot we have and those blocks, it would be very beneficial if we could have as little positions to build a house or a wall with the robot as needed. So we save the time for moving the robot and for recalibration and so on. And then where to place the blocks and the robot in the house. Because here you see the ground is optimal. But when you have ever been outside watching how a house was built, everywhere, hoses coming up, sticking up from the ground. So you need to define places where to put the robot. And then, where to put the blocks so that we also have the possibility to reach as many blocks to not move more than necessary. So there were very many questions which we could solve in an algorithmic way. But how to bring it out? So, next slide. First experiment outside. Very interesting. So we were bringing the whole thing outside, driving around, having the controller in a house there. So then to guarantee stability, put out the legs. And then putting blocks in a saw, for example. Sawing it into the right size we need it. And then also performing the mortar application with this robot, with the nozzle connected to the end effector here. So there it was important, we just had to applicate on the stone part of the blocks and not really on the isolation, because it doesn't have any value. And then place another layer of blocks on top. And the nice thing here is, it is really, so they are called Finia exact blocks. They are really exact in comparison to the bricks. And you just need to place a first brick, and then, in relation to this, everything is calibrated. So the first block is our calibration stone. This was really good. And regarding logistics, so how to bring it out. So we had a container here, filled with all the equipment we needed, and also special place for the controller inside the container and so on. So things which stayed during performance inside the container had a specific position, and other things had a specific place to be stored in. And then we also had an event where we handled those type of bricks, and we have built a fireplace outside at the Science Village Center in Lund, close to ESS. You might have heard about that. I have a link here to a video, but to my feeling right now, I think it will crash the connection. So I leave this out, but I can send it around later. So it was a documentary, a 1-minute news about the day, seeing what we are doing. But it was a 2 hours building process, and we were there 2 days in advance to just bring everything out, the day in advance to set everything up, make a first test, and then the whole day to perform. And while we were performed, so we had put mortar on every layer of bricks, I took care of the mortar on this day, and I did nothing else than 2 hours mixing mortar and filling it so that the robot could work, and this without a break. So you see, so there were so many processes around it which need to be automated, and not just the main process, and also this preparation work, and another day to clean up again. So for 2 hours event, more than 3 days of just close preparation around. Then I have something you might like, since you are very interested in these humanoids, I know. So here we have Spot Robot. And what was it able to do out of the box? this was nice. So we got it, and you made the first test because they said it was able, if it's equipped with the arm, to open door handles. And you see, so it's scanning and scanning and scanning. You think, let's see. It looks like a snake. And then it has it found the door handle, opened the door. Then it didn't know what to do. So, yeah. Then we thought, oh, maybe. Maybe we need to tell it a little bit more. And the pendant we had for it, it was a little bit more like the Nintendo Switch. So you could control it and just push, go through. So kind of buttons on a smart interface. And then a few more tries later, you see on the right, in another perspective, Spot was able to find the door handle, open the door, and to go through. Yeah. Then it didn't know how to get rid of the door handle again, so, but it managed in the end. And this was inbuilt out-of-the-box functionality, which for me is really, really cool, because this is not trivial. This is really, really complex. And I don't think that other things, so if you buy now a humanoid, I cannot imagine that it cannot do anything if you buy that. So it must be able to do something. But what to do with such a dog now? So it's nice, but I don't need a dog at home to open a door for me. So we thought it's maybe good to have it on the construction site for visual inspection. So to walk around, take photos, and then compare the everyday state with the planning. So if it's really built like intended, or if they was built something differently. Because then you can, I know we all know those airports built and then not opening because something went wrong. So this happens. And here, then the costs are too high if you detect it too late, right? So here it is good if we thought we could just walk around, take a picture. And one colleague, so he had written his master's thesis on this. He really made a good thing. And here you see, what would you expect? You would not expect it to handle like a 3-year-old and just walk into the hink. So you would have expected him to walk around. But this was not possible. So this was a little bit what we haven't expected. So because I thought those kind of sensory is really far in development to be inbuilt. Yeah. But now you have seen this too, just so it's a long video, 9 minutes, but I don't want to show you 9 minutes a walking dog around. So, and project partners. In construction robotics, we had, of course, so the funding was Smart Built Environment, Bovacat and SBUF mainly. And then we had a lot of companies from the construction industry, like PEAP, Cementa, and the architects, FOIAP. And we also had, us as the university and also a robotics company with on board. But what happened then? Then my 4 years of postdoc were over, and I would have needed a permanent contract. We tried to get funding, we didn't succeed, so I needed another job. But what to do? I thought maybe it could be good to do something else, maybe something a little bit more routine day. It's good with a family with small kids. And so I started my work as a tanks and vessel specialist at Tetra Pak. It was good. I had my first permanent contract, very structured days. The work was challenging on another level, but somehow it was a little bit, so it felt like I lost this kind of freedom I had earned when I started to study. So maybe it was not the right thing for me. But then I got a call from a friend of my husband looking for somebody else at Alfa Laval. And then I joined Alfa Laval. So it was like, it came luckily to me, and then I could join, and now I'm here. So this is really good. So I stayed 1 year at Tetra Pak. So the environment was good, so I had good colleagues and so, but it was just another kind of challenge and maybe not fitting to me, so I fitting to somebody else. But at Alfa Laval, there is really a lot to understand before you can really work. So the organization, the products, there is a lot around. And this, so I have a small Uppdrag today to show you a little bit the company too. So we had a visit from Macron. It was before I started in January 2024 on the Lund site. so where we build the heat exchangers. And you see the world's largest heat exchanger factory. So it's a really big site. And the good thing is, I think the French people, they also like these nuclear power plants, but they have they have a challenge in the summer because it's getting too hot and the cooling water is not there to make energy with this kind of technology. So they need to look for alternatives too. Alfa Laval. So a few of you are knowing this slide already. So this is our site. We have those buildings here, the white one, the brownish one, and another one in the back, where we have our offices. We have a competence lab here. Then here, this is the whole production area. Then we have assembly next to it, a tool workshop, a new one, a lot logistics for the finished products to be transported, an innovation center here, and also a gym. So that's a really big site, and with a lot of competencies. And the company itself is more than 140 years old already. We have many, many employees, more than 22,000 employees. And also there are some patents outside. And there are 3 key technologies. So we have heat transfer, separation, and fluid handling. And you can find Alfa Laval almost everywhere on the world, at least sales companies and service centers. Just Africa is a little bit not so visible, I think. And so Alfa Laval sees different challenges for the world, and one of it is energy transition, which I think is really relevant today. Then we need clean water, sustainable food, which belong together somehow, and then the marine transportation, because this has a really big CO2 output. And based on those challenges, they have built 3 divisions. So we have the energy division, where our team is located in. Then we have food and water, and the marine division. And we serve most industries. Sugar fabrication, chemicals, food and beverages, metalworking. You can just have a short look over it. I think, it's really a wide range of industries where you find our products. And the key technologies which make it possible to be in all those industries is heat transfer, of course. Then we have separation. For example, if you produce milk and you want to separate into the milk which you sell to people and the milk you keep for your calves later to make more milk cows again. And fluid handling. But what are we doing there? So why are we there with automation and robotics? So in this team where I am now, so we are right now 8 people and a manager. No, we are 9 people. A manager with a team of 8 people. And we have different competences. So we have people for PLC programming, we have people for robotics, then we have someone who is investigating, or 2 who are investigating AMRs. Then we have simulation, could be robotic simulation, could be plant simulations, different kind of simulations. We have projects looking into how to implement AI and machine learning, how to get this into the company. We have also possibilities to make our own construction design if needed. So that's not our main competence, but we can do. And machine connectivity also. And one colleague from me, he's very into vision integration, which is really good to have inside the company. And how do we work? So, or where do we come into play? So sometimes, the company, so we are in a global team. So we are located in Lund, but we are not just responsible for Lund site. So we are also responsible for other sites. And every business unit has their own OD group for products, for a specific product group. And if they find something, or we find something together in discussion where is no automation solution yet, we can discuss it, and then we can start and try based on existing technologies or also on new technologies or combination to set the solution up. So we can start to set this up in lab facilities, which we also have in Lund, just 2 kilometers from our main building. So, and when we have reached a specific state, so a specific TRL level, the OD from the specific product group comes into play, and we try to give it over to them so that they continue within their own product group. But this does also mean that this product group needs to have the competencies in-house to continue. And on some sites, this is a little bit easier, like the site where Will is working, because they have a lot of competences in-house. And on some sites, they don't have specific, for example, robotics competences in the product groups, and it's a little bit more difficult. But until this is beneficial, it's a long way, because it first gets to be beneficial when it's really up and running in production. And this is a long way sometimes. But what do we have for challenges for automation? So our products, you have seen, I think you know, heat exchangers now and separators, for example. So our products, they are made of steel. Steel is shiny, so it's tricky with the vision sometimes. Then steel is not like whatever material. I don't find a good comparison right now, but it's a little bit, it can be bended, it can have tensions, it is very variety, have a lot of variations. And then if somebody orders, for example, a heat exchanger, it's always a customized order. So I don't think we sell the same configuration again and again. So it's often you can independently what you need, the amount of plates could be different and so on. The sizes, we have a very high range of sizes. So the smallest one I think is a little bit bigger than my phone there, and the biggest one we have is 3.5 meter high, 1.5 meter wide. So a big variation. And then also the way of building, so other materials in between to get it tight, and also the structures of the plate. So there's a lot R&D around the plate design and around the materials we are using, a lot ongoing. And then the products itself, so they are really complex also, and sometimes also they are sharp, so they are not super heavy, but yeah, sharp, I think sharp is the worst thing. So object handling is an issue, decision taking, so how to solve something with algorithmic problems. So those are the things we are trying to handle right now. And then also what we are part of MARC now, connected to Jessica's research area, the smart and portable automation. And we have started to scout for use cases in the company, and we have found many use cases, and we have been in touch with many sites, and there was a big interest of being collaboration partner and bringing something into the project and also getting something out later. And there are challenges like, so how do we make this inaccuracy handling during robot execution, so which I think is a good research topic. How do we feedback information from inline quality checks so that we maybe adapt the robot program according to the outcome. So there are a lot of questions which we can really put into real research environments. Could a portable factory look like, a portable multi-robot system, whatever, and how can we implement it on different sites where we have different PLCs in place? How is an easy integration, a plug-and-play integration possible? But there are also tasks which are more common, and I think everybody has to handle, like the programming itself, or safety, certification, calibration. How can safety look, which does not limit me so much? So do I need a fence when I don't need a fence? So what does it mean for me? What is the productivity, the effectivity? So there are many, many questions to handle. And yeah, this I just leave open, because I think that we can discuss many more hours. So we did already, but there are more hours to discuss. And now what I already said in the beginning, since May now, I'm affiliated to Mälardalens University. so I can join a little bit more here and being involved in the research you do, being more in touch, which I think is really good. And we can also offer that, for example, your PhD students can come to us at Alfa Laval and work a little bit there, which I think is also a very good opportunity to be more in the industry. So be connected really and sit there and get the insights you don't get when I just explain something, for example. But what did I take with me from all the things I worked on? So I think we had two main challenges, I would say, over the way. And this was quite often, so how do we get the silent knowledge? How do we transform it into robot motion? So all those details, the manual labor includes, and how to identify processes where automation is needed, and how to decide if it should stay manual or maybe be a hybrid process or a fully automated process. So these were all the big challenges to handle. And what about sensory integration? What do we need? How does it work easy, fast? And how do we handle process variations? So if, color, haptic, so what to do and how to handle those inaccuracies which can happen if you have other light conditions and they get another values from a sensor because now it's affected by light and so on. But no, thanks. Thanks for your patience.
Thank you, Mike. I
Thanks
think
for
we can
listening.
give you applause. And we open up for questions or comments. So, anyone? Still a floor. Any questions?
I have one question. So what's the biggest difference that you experienced on how you work with in Alfa Laval, so in this sort of like a pipeline for a project? How to get them sort of progressing in maturity compared to academic research?
I think I told this to somebody yesterday already. It feels like so in research you need to put a lot of energy before you can actually do something. So all this acquisition of partners, networking, what you have to do, this comes all before you can start the actual work. And since I have started at Alfa Laval, it is so the base is there. You can, if you have an idea, to get something up and running, it's pretty fast in comparison to the processes I got in touch with in academia. So this is a big difference.
Thanks.
We are working together in MARC and smart and portable automation, also other research areas. What would if you, and this is a long project, 8 years, if you would envision the benefits for Alfa Laval from this research profile and the collaboration with the university and the other partners, what would be your dream results?
What we get out of it.
Yeah.
So to me, I think it would be nice if we can really have more intelligent systems, so smarter systems where we can really use the feedback from inline quality control and feed it back to the robot system or the other peripheral devices we have on the side. So if we could enhance this information flow in the machines, so also a little bit more machine learning implementation, because I think we have the calculating power, we also have the knowledge inside. So if you give us a direction, we can connect with other people which have more knowledge than me, for example, in machine learning, then we can get things up and running, and that we can benefit maybe from standards which we can put into the company, so that it is much easier to set something up in an environment and we don't need to start from scratch always, so that we can enhance our own standards so that the entrance is easier for new projects. Yeah.
Any more questions from the audience online? If not, we thank all for listening today. Thank you, Michael.
Thank you. Yeah,
Good. And then we close the session.
yeah, perfect.
Good.
Yeah, thanks a lot online for listening.
Thank you very much.
Yeah, thank you very much.
Thank you.